Okay, bang on time. Welcome to this morning session in which Andreas and Konrad are going to tell us about the challenges of dealing with WebAssembly as it grows from a tiny, tiny language to this monstrous thing.
Yeah, thank you. So, yeah, somewhat unsurprisingly, I'm going to talk about WebAssembly. And for those in the room who don't know, just a very brief recap what WebAssembly is, or WASM as most of us are calling it usually. In a nutshell, it's a low-level virtual machine, in the same sense that the JVM is a virtual machine. And it's low-level in the sense that it doesn't have any high-level like language constructs built into it, like an object system and all classes like the JVM. It's more like, in the first approximation, if you want, like a virtual ISA. Of course, somewhat more slightly more high-level than a true ISA, because we also have to maintain all these important features. Because WebAssembly, as the name might tell you, is running in things like the web, but also various other ecosystems like it's used for edge computing, it's used on blockchains, it's used in many different environments these days. So these properties are kind of like really crucial and the value proposition of the thing. But in the content, yeah?
So WebAssembly is a language?
Well, anything can be viewed as a language, and naturally...
You said it's language neutral, but then it's a language.
Yeah, but...
It seems like a contradiction in terms.
Well, language neutral in the sense that, unlike the JVM, it's not like designed to support some source language particularly well, right?
So it's a target.
It's a target,
It's
yes.
just a virtual machine.
It's a virtual machine, and it's kind of like, yeah, low level, and it's an abstraction over the hardware and not over some source language, right? That is what distinguishes it from things like the JVM. Yeah, and in the context of this event, of course, the most important part, it's actually fully formalized. And that's what I want to talk about here. So we have seen a couple of formalization of ISAs this week, and the WebAssembly formalization has a number of significant differences to that. So first of all, it has been formalized from the get-go, right? So the formalization was actually an inherent part and still is of the whole design process of WebAssembly. So it's not like an afterthought that some academics did, like after the fact, re-engineering, reverse engineering what some industry people did, but it has been there from the beginning. And equally important, it's not just something on the side, it's actually a normative part of the official W3C standard. The whole standard, the specification document for WASM, is built around the formalization, essentially. It's a central part of the standard.
By formalization, do you mean that there is like a bunch of semantics rule written on paper, or that there is something in a formalism like a proof assistant or whatever?
That's what my talk will be about, essentially.
Okay.
What I exactly mean by that, right? So, it's an end-to-end formalization. So unlike some other like programming languages, perhaps, that have been formalized or have a formalized semantics, we are really formalizing everything from like decoding bytes in source code or the text format to really every single bit that is changed during execution in memory or in registers. And the semantics, also importantly, is almost entirely deterministic. So this is important to achieve portability, but also for safety, security reasons. In particular, I mean, there's slight, minor bits of non-determinism, but there's no undefined behavior whatsoever. So that is really important. And that includes even things like the relaxed memory model that does not exhibit any undefined behavior. It exhibits non-determinism, but not undefined behavior. Although I'm not going to talk about that here. And another crucial difference to the other kind of specifications we saw this week is that the WebAssembly formalization uses like a textbook style of programming language theory, right? It's really just using declarative formal semantics in terms of typing rules and small step reduction rules. And a syntactic soundness proof like you would you find in a paper on programming languages. And all that is intentionally simple, right? So we're not trying to do anything fancy here. So if you've read like the first few chapters of Benjamin's book, then you should be able to understand the semantics and formalization of the semantics. And that is very much intentionally so. So we really want to be accessible to people. And it also has been mechanized in both Conrad and Isabel, and Konrad will be saying much more about this. And you could argue it has been successful in the sense that since the publication of WebAssembly as a standard, there have been no serious spec bugs found, nor have we discovered any disparities between implementations. And I mean, it's hard to find exact evidence whether that is due to the formalization or due to the test suite or other things, but at least with WebAssembly's formalization being an inherent part of the design process, that led to a very tight feedback loop between design and formalization that and made WebAssembly both simpler and cleaner language for that, right? So at least there has definitely been an indirect benefit of that. Okay, but this kind of setup means that the audience for the WebAssembly formalization as part of its standard is quite a bit more diverse than the things we've talked about before, right? So what's the audience of a standard like the one for WebAssembly? Well, you have the kind of expert readers, right? Like academics, for example, who really understand formal semantics and want to do meta theory or other things, maybe proving stuff about programs. They really want a formalism, and they want an effective formalism. Then the much larger group is actually just like casual readers, maybe programmers or developers, software engineers who are interested in understanding the semantics of WebAssembly. And usually you can't assume they understand formal semantics, right? So they want plain English. So a completely different presentation. And then there are implementers of WebAssembly engines as well as compiler writers targeting WebAssembly. And typically they're sort of in the same camp. Very few of them, unfortunately, understand formal programming language semantics. So they also need plain English. So this side is kind of like the people who consume a standard, and then there's the people who kind of produce it, right? So in the WebAssembly context, that means spec authors, which initially was me, but also people writing proposals for additions to WebAssembly. And then spec editors, they are responsible for reviewing the stuff that the other group wrote, right? And that is a very small group, it's almost singleton. And then there are people who want to do mechanization. They still have kind of other desires about the specification and the formalism in particular. So yeah, lots of diverse requirements in a way. So what challenges does this produce? So first of all, really the standard has to be accessible to a large audience of people that have no formal training. I said that before, right? So we really need plain English as well. I mean, formalism is all great, but it's not enough. But even the formalism itself, we want it to be accessible in the sense that, what I said earlier, we don't want it to require learning some weird alien invented formalism that nobody has seen before, but really we wanted to use standard textbook techniques, right? And part of that was also my mission to kind of prove that these standard techniques that we have used in academia for 30 years actually work, and they scale to an industrial standard product or system. And then, of course, the authors of proposals, they have to produce both of these formulations, right? And they usually also have limited formal training. So at least in simple cases, we want to enable them to even write that stuff, including some of the formal stuff, essentially by copy and paste. So if somebody's just adding a bunch of new instructions that don't do anything difficult structurally, then they should be able to understand how others work and just copy that and modify it to their needs. So that is another part of it. But obviously more complex features which cross-cut the semantics add something interesting structurally that usually will require help from experts. But yeah, I already said that sort of whatever change we do, there are mundane requirements that we have to be able to review these things efficiently, right? So we use GitHub, everything is done in terms of pull requests and code reviews on GitHub, so that has to work. So we need a format that lends itself to diffs, for example. And of course, something like mechanization is currently not something we can expect from authors of proposals. So that is really left to experts like Conrad and Philippa's group. Okay, so to give you an an idea what the spec actually looks like, this is kind of like one page from the spec, right? This is specifying a bunch of instructions, and you can see that it's like, it has these formal rules there which really look like very much like you would expect from a decent paper. But interspersed with that is all this prose, which tries to kind of say the same thing in natural language for some definition of natural. And that is the validation, the specification of validations for typing rules. Yeah?
So I'm curious why you chose to work with inference rules rather than, for example, a definition interpreter or something.
Well,
might be even more accessible.
Right, but then meta theory is much harder, right? So we also want to show that you can apply all these methodologies and techniques that we have in programming language research and theory, that we can use that here. And we have a soundness proof, for example, right? Which is totally standard approach.
So to follow up on that, I mean, if you're going to do this work in the meta theory, again, the mechanization might help you because then you could use the tool to do the meta theory.
Yeah, I definitely, I mean, we want mechanization, but I'm going to get to that, right? So that's kind of one of the consumers.
I would say there are also a couple of other answers that kind of warded us away from a definitional interpreter. Firstly, there are corners of the WASM semantics that are actually non-deterministic, and that needs to be represented faithfully.
Yeah.
And secondly, you now have a very complicated object type system that needs nice inductive rules.
Yeah, I mean, with WASM 3, type system gets more interesting, and you have all these problems you usually have in languages. Right, so yeah, this is like the type system essentially. And then the operational semantics, similarly, you see small step reduction rules over some definition, like triple of configurations like you would expect in a paper. But again, you have this prose in here. Oops, sorry, that was the wrong button. You have this prose in here as well. And that is a quite different representation of the same thing. It's more like algorithmic. It's talking about popping values, pushing values from the stack, things like that, which is the kind of thing that these like more casual readers would expect, right? Because they're familiar with this from other language specifications, and they understand that. So this was kind of like a very simple page. There are, of course, more complicated rules. This is like a medium complicated one for table branch. So actually the declarative rule is still kind of nice and simple, right? But once you go to an algorithmic formulation, it becomes a bit more verbose and repetitive. And that's also one reason why if you do definitional, then everything becomes this, right? More or less. Maybe not as verbose, but it's like not as compact as a nice declarative specification. And again, similarly with the execution rules. So you can see that there are some interesting things going on here, right? This is like more complicated, but also where declaratively you just have two rules. In the prose semantics, you kind of have to merge them into one with a conditional in them. So it's a non-trivial refactoring. But yeah, the summary of that is we have math formal semantics, which is declarative, and we have an English semantics which is algorithmic. And of course, the idea is they have to be equivalent for some meaning of equivalent. Yeah.
It's a little hard to read the text from back here, but it looks like some bits that are repeated.
Some bits are repeated.
Do you mean in the formal rules or in the prose rules?
In the prose.
I think it's the next one where this appears.
No, also here. For example, for each operand type, T blah blah in T star, that line appears twice, doesn't it?
No, this is for each operand type, and this is for each label. These are different loops. So we are using like this star notation, which is essentially overbar notation.
The point is, it says for each operand type TJ in T star, and then a few lines down it says the same thing again.
Okay.
You need to do the iteration. You need to do the iteration once for the label list and once for the default label. That's
Right.
the problem.
Yeah.
We could have done that differently. We could have represented that as one non-empty list, and then you could have eliminated that one.
Yeah. So yeah, this is kind of an artifact of this specific rule, but yeah, but this is actually an important part of the kind of meta notation we're using. We have this star thing, which is kind of like it's essentially an overbar. but a bit less cluttering, and then this turns into loops when you do the prose version. And sometimes you nest these things, right? Like here you have an outer overbar and an inner overbar, and that's why you have nested loops here.
So it's a propositional transformation from the schools of English?
Ideally, yeah. So I mean, I did this manually, right? I wrote I started writing the formalism, and then I produced the prose like in a kind of manual fashion using some design patterns I had in mind.
The algorithm is you.
The algorithm is me, but it's intended to mirror what you see in other standards. But yeah, we are now trying to automate that. So, okay. Yeah, here's another example of a select instruction and its execution semantics. And what you actually have to write as an author is all of this, right? And this is like still a fairly simple instruction. So there are cases where you have pages and pages of this like markdown stuff and manually raw LaTeX, because our tooling doesn't actually allow you to use any LaTeX package whatsoever. We even had to hack it to even have macros at all. So that was kind of annoying. So it's not pleasant to write all this, as you can imagine. But it doesn't stop there, right? We have other formulations of essentially the same. So there's a reference interpreter we also have, which is written in very stylized OCaml, which is another like hand translation of the paper rules into OCaml that very much are intended to look like the paper rules. So it's a very particular style of OCaml that you usually wouldn't write, but it's meant to be an executable version of that formalism. And then there's, of course, a huge test suite that is written by hand. That's in the WASM text format. And that's also manually done by authors and implementers. And coverage of that is varying quality, I should say. And of course, there are the mechanizations, which again are like equivalent formulations of the same thing. And we have two of them, right? Yeah, Peter.
It's a cultural question. Having observed and trying to keep the RISC-V community over the years. So they started out saying, any extension, it has to come with a formalization and a test.
Yeah.
Pretty quickly, that transition to all the extensions we really want are allowed to have waivers. So,
What?
Waivers.
Waivers.
So, what would you say about the social process of getting people to actually do that?
Yeah, I can say a little bit about that later, but it's definitely, it has been a struggle. I mean, first of all, getting people to accept the very idea to have a formalism in the spec at all was not an easy fight at first. But it all comes down to key people supporting it, usually. And so far, we have managed to hold the line with respect to keeping this requirement that every new feature has to be formalized. The proposal champion is responsible for coming up with the formalization.
Because I'm specifically, that is a great thing, I'm specifically thinking about getting people to write the tests.
The tests? Yeah, that's an excellent point, because actually some of the proposals I've seen, I have not been happy with the quality of the tests. And I think, I mean, so we have a committee, right? And we have a voting process, and there are various requirements for advancing a proposal to the next stage. And usually that should be captured by that kind of thing. So where people say, yeah, but this doesn't really meet our standards and we can't vote it to the next phase or something. But sometimes this process is slightly failing. So it's not super reliable. Human factor, right? Right. Okay, so yeah, and this is again like a manual translation into the mechanized form. And when you then nicely prove some nice results like soundness about the mechanized semantics, then how does this transfer back to the paper semantics actually? All you have is this like eyeball correspondence, right? And you have no real way of guaranteeing that these are really in correspondence to each other. So yeah, overall you have all these artifacts that we have to produce at some point or the other for WebAssembly. And in some way, they're meant to be equivalent. So there's a lot of redundancy here, obviously. But it's worse than that because it's not something we just did once and now we're done. WebAssembly is actually growing pretty fast. And to give you an idea of that, here's are some numbers. So WebAssembly 1.0, which is now 7 years old, actually is kind of pretty nice and small language. Spec has 160 pages. There are 170 instructions, not that many, right? And even fewer rules to define their semantics. With WASM 2.0, that already increased quite a bit. In particular, the number of instructions more than doubled, and almost all of that is due to vector instructions. That's why the other parts didn't increase quite as badly. And with WASM 3.0, which you're kind of close to completing, that is what is in the current draft. There will probably be a few more in the end even. So you can see quite a progression here. We are now around 500 instructions, and as I said, the process for that is based on proposals. So if you want to see the timeline here, with each version of WebAssembly, there were I don't know, half a dozen to a dozen proposals merged into the standard. But there are way more in the pipeline, and probably not all of them. Maybe even a minority of them will finally make it into the standard, I think. But still, this is a repeating problem, right? All this repetitive work we have to do. Yeah, Peter was first, I think.
There's a question about what kind of planning for the future one does, Andrew. So the ARM semantics, the ARM architecture is evolved over many years in a not totally dissimilar way. Pressure from customers and whatnot. And its PDF is now a delightful 14,777 pages. And you can imagine the pressure on WASM to include the triptychs and whatnot. Will, over the years, push it closer to that.
Yeah, that's my fear too.
So the question is, to what extent can one push back on scale?
That's a very good question, and of course we had discussions about that. So I'm usually the person who pushes back on proposals, and because they are maybe too complex, too ad hoc, or just these one-off things, or they don't have a particularly well-defined semantics. The one thing I'm particularly unhappy about is this relaxed vector ops, which is now introducing implementation-dependent behavior into WebAssembly, and that was all pushed by people think that machine learning is important. So there are politics around that too, and there's a lot of pressure from various directions to add stuff, and you cannot always resist it, unfortunately. I would like to resist more, but in the end, it's kind of like a process. I think you were first, right?
Existing garbage collectors or exceptions, are those things mandatory in WASM? Will it be included for sure in 3.0 and you have to use garbage collection, for example? And if that's the case, how do you handle the...
No, you don't have to use it. Any of these features, I mean, a user can ignore all the features they don't need, right?
And so you have a modularity question with your semantics, right?
Right, so that's coming down to a discussion we're also having. So there are quite a few features which some platforms that want to use WebAssembly won't be able to implement. GC is something, so WASM is used in embedded space quite a bit as well now, maybe surprisingly. Where you probably don't want to implement garbage collection, right? Or then you have systems that can't support threads because of non-determinism, like blockchains are a good example. And one thing I've proposed is that we also adopt the notion of profiles that allows you to properly define subsets of the language that exclude certain features. But there's quite a bit of resistance to that in certain parts of the community, actually, because they kind of want to live in this dream world where everything implements everything, which I think is completely unrealistic and not what we are seeing in practice.
Sounds like C. That sounds like C.
Perhaps, yeah.
Also, the standards committee is very much against having variations of the language.
Yeah. But I think it's a trade-off between, having a broader standard that supports more diversity in clients, or just having a narrower audience. And I think you really want a broad audience, right? And then you have to cater to their needs to some extent. But of course, it's a compromise.
This is also
Yeah, yeah, and right, and that's of course one fear. So you don't really want like this super fine-grained kind of optional features. You want very coarse-grained features. Yeah, so I think I already said that. Oops. Sorry.
What you said about C, right? The standards committee doesn't like that and ignores it, and then all of the embedded implementers go do these freestanding profiles things that are just kind of around that, and they don't engage very well with the standards committee, and they have completely unconformant implementations that cause giant problems for everyone. I think it's just the idea to avoid that.
In C and C for voice, you also have all these kinds of compiler flags like F,
exactly.
aliasing,
The reality is that WebAssembly engines also have all sorts of flags nowadays for like turning on and off certain proposals.
But they are not standardized.
No.
And this is the argument for the profile system. Right?
So just one, I have to hurry up a bit. So just one data point more, like some of these proposals are really large, like the vector types, vector operations. That was a diff of more than 100,000 lines to the spec repo. Most of that are tests, and most of them are like generated, but still it's like at least 30% of that's handwritten stuff. So there's a scalability issue clearly. So that raises all these practical questions like how do we reduce the workload, obviously, and how can we improve the effectiveness of code reviews, because when you're faced with 100,000 lines, that's kind of impossible, right? And the coherence of the specification, and then the thing I mentioned earlier with the paper semantics and mechanizations, how can we reduce the gap between them and minimize errors, and all these practical things you kind of want to solve in a real-world standard. And the answer usually, of course, is, well, we do some kind of tooling, right? And in this case, we want a DSL for authoring the specification. And that's what we call WASM SpecTech, for lack of a better name. And that's kind of what I want to talk about in the rest here. And the idea there is that we have a DSL, and that's going to be the single source of truth for all the definition of the language, and all these artifacts are generated from that. And that's work that involves quite a few parties here, KAIST and Imperial, Philippa's group, and Conrad, of course, is involved. Sam Lindley is also involved, so a few people are in the room here. And lots of students, too. Too many to name them all. Okay, so we want this DSL, but again, there are various real-world constraints we have to live with. So first thing is, we already have a standard, right? And people are using it and used to it, so we can't like completely change that. So the tool we're doing has to generate something that looks close enough to what we already have. It's one constraint. And that includes it has to produce natural language, right? And another dimension is like for authors of the standard, they tend to be already overwhelmed with like having to write formal notation. So we don't want to force them to learn yet another like formalism or language. We kind of want to at least approximate sort of like a WYSIWYG user experience there. So they kind of can write what they later expect to be rendered or generated. And yeah, we need to make that possible, we need to support all the meta notation used in the spec, and we have to support code reviews properly, so we need kind of a DSL syntax that is differently. And one big constraint also is because the spec is like big already, it has to be set up such that we can port it over incrementally. And that actually created a lot of additional work and friction in doing this. There are more constraints or maybe more like goals in this case. Of course, once you do that, you want as much automation and error checking as you can get. And the idea here is that we really want to leverage the fact that we are writing a tool for this very specific use case, right? So we really want to specialize it to our use case, specialize the hell out of it so that it can sort of leverage the specific domain knowledge that we have here, and thereby like drastically simplifying the problem which we have to solve here. Like unlike more generic tools, like maybe OT or something, we can cut many corners because we know what we're dealing with. Right? And then there are, of course, again, these practical constraints. We really need to own the implementation because we need to be able to maintain it down the line for many, many years to come, right? So we can't really depend on something that has an unclear future. And we also need to be able to tweak it fast. Whenever some new feature comes in that we can't yet support, then we need to be able to. But I should also mention that we don't want to build another theorem improver, right? So this whole thing is really just meant to be sort of like a preprocessor or processor of kinds. Okay, so the idea is that instead of writing this to produce this, in a nutshell, what we want people to write is just this. So really, this is just an ASCII rendering of the formal semantics. And that's what our DSL will look like. And from that, you can then generate this. And ultimately other things like the cork formulation as well, using different backends. So quickly running you through some of the main concepts of that DSL, it should be largely unsurprising in many ways. So of course you can define abstract syntax. So for WebAssembly, for example, these are essentially like type definitions if you want, right? Sort of what you would expect. And to support like custom rendering, you can attach some hints that tell the LaTeX renderer how to like show this on paper, if the syntax doesn't quite cover it. And then the essential kind of concept there is the concept of a relation, and that's a very generic concept. You can just define relations, and we use that for both typing and execution. So as an example for the typing relation, well, first we define a type of context, of course. And I'm simplifying here just to give you an idea. And then we have the typing relations for instructions, for example, which you can write out as kind of you would expect in ASCII art, right? If you're familiar with programming language notation. And then you write rules for that. And these are like a couple of simple rules. Like, for example, a select instruction that expects 3 operands on the stack, 2 of which are of some arbitrary type, and it returns 1 of them. You can also have side conditions on these rules. So here, it's not like an inference rule. It's kind of like an inverted inference rule, if you want. You write the premises below the conclusion. And some of the rules are also inductive, of course. So if you have more complicated instructions which are structured, like block instructions, then you have a premise here, which is another invocation of one of these relations. And in a similar fashion for reduction, so as I said, we just define a structural operational semantics, small step reduction rules, and for that you need to define kind of like your configurations. So I won't walk through all of that, but configuration is this triple I mentioned earlier. So part of it is the store, and then you have a stepping relation, which goes from configuration to configuration, like you would expect, right? And here I also define like a shorthand, which is a pure step, so that just avoids some clutter. In cases where we don't touch or modify the store, we can just define it as a pure relation over instructions. So as an example, here are the select rules you already saw earlier. They are like in the pure relation, and you write them out as you would expect. And here's one that actually uses the store, like looking up the value of a global. And here I'm using another feature of the DSL, which is I can define kind of like auxiliary meta-level functions for looking up stuff in the store. And in that style, you can define the whole thing. And yeah, but the important part is we can now generate stuff from that. So first of all, yeah, we can render both the prose and the LaTeX. So here's another kind of example, a couple of rules for reduction. And what we can generate from that is now this. So both the LaTeX, which really looks like the rules, and the prose is entirely auto-generated from just this snippet. And it's not totally perfect yet. There are still kind of some things we want to fine-tune, but in general, it works. To give you a taste of that, here are 2 versions of the execution semantics for the select statement, and as you can guess, the left-hand side is the handwritten form, and this is the generated form. They're almost identical.
Do you somehow bake into
the specification language, the fact that you're specifying a stack language?
No.
So how do you generate the pop and push?
Right, so that's an excellent question. So we have different backends, right? I'm going to show the architecture in a minute. And one of the problems with this approach is that the different backends have to make a different amount of assumptions. So for example, the LaTeX renderer, that doesn't make any assumptions whatsoever. It just uses some of the hints you can sprinkle. The prose generator, that goes through a process of transforming the whole declarative semantics into an algorithmic one, and that has to make various assumptions about how that works. So that bakes in way more assumptions than other parts. And I mean, in principle, that's inevitable. Right now, there's way more baked in than I'd like to, and some of that we would like to factor out into also like annotations in the source, like this is a context, for example, and that doesn't hard code like the type name context defines our context or something, more like things like that. But yes, this is one of the kind of problems that we are facing. How do we cope with these different amounts of assumptions? Right. Of course, in the process of doing so, we discovered some bugs in the spec. I don't want to bore you with going through all of them. So if you're interested in that, you can look at our PLDI paper. But obviously, like most of the bugs were in the prose, right? Because it's so laborious and error-prone to do the hand translation. And these are now just basically gone by construction, right? As long as at least the code isn't totally bogus, we are not producing incorrect prose anymore. And there were lots of typos even, and more like trivial things. But we can go further. So coming back to what I just said, so to actually generate the prose, we have to do this transformation from declarative into algorithmic, right? And this is kind of reminiscent of process that's known, I think, in the Isabel community as animation. So we're adopting something similar. And the result of this transformation is internal representation that we call the AL, the algorithmic language. And you can think of that as an AST for the prose. So from that, rendering out the prose is then just kind of like a trivial pretty printer that somehow does English, right? But the nice thing about having that is it's a language actually, and we can run it. So one thing we can do is we can interpret this AL, and doing that we can now read like the specification, or one specification for WASM. We actually have different ones for the different versions, and run that on some input too, and that why we have like a meta interpreter for WebAssembly. And that happens to pass the entire test suite. So this gives us a very high level of assurance that our semantics is actually correct. And in particular that what you see in the actual document is correct, right? Because there's a one-to-one correspondence between the AL representation and what's rendered into the document. So the overall picture then is something like this. I mean, it's essentially like a compiler infrastructure, right? So you have some pipeline, wrong button, sorry. So you have the input, which is the spec-tech definition of the semantics and the syntax too and everything. I didn't show you. You can also define the binary format in that. And you go through various intermediate representations, and from that you can like produce it in different steps like these, generate these representations. And then you have the interpreter I mentioned, which you can feed the test suite. And then you have this nice property when this succeeds, then I can assume that the prose that I see in the rendered document is actually correct. And in a similar fashion, once we do the proofs in the cog theory that gets generated, so we are not quite there yet, we have not ported the proofs from the handwritten mechanization to the generated one yet. But once you...
We've done preservation.
Yeah, so there, I mean, we're somewhere along that. But once you do that, you also have assurance that the actual formalism you see in the actual document is correct, because it all comes from the same source, right? And it's all auto-generated from the same source. So there's at least some kind of assumption that as long as there's nothing completely bogus going on the way, you can kind of transfer back morally the results. Yeah.
So do you need to help the tool to figure out how to turn the operational semantics into something algorithmic? Like, for example, for guessing execution context and that kind of thing?
Yeah, so we have this hint mechanism that is used for some of these things, but as I mentioned earlier, right now, most of these things are kind of hard-coded into the prose backend or the animation phase actually, and I would like to reduce this amount of hard coding. It makes many assumptions about the actual input that it shouldn't really be doing, and more of that should be shifted to hints or something. Yeah.
Do you have a formal semantics for AI?
So I think they're actually, like I saw various commits, so that part is mainly done by the Keist folks. So they have been working on at least writing a validator for that. So I think they have some semantics in mind, but it's not like written out yet. We also don't really have a semantics for the IL. This is one of the things I'd like to do in the future, right? Like, I mean, you could view that as a meta theory of kind and write out the semantics, but that is like, right now it's just a preprocessor. Right. Yeah.
There used to be a tool called OTT a long time ago, I guess by Peter and others,
Yeah.
with similar goals.
Right.
Can you compare?
So, yeah, I mentioned that earlier, right? So one of the reasons here, or one of the routes we took is that we really specialize to your use case. So we don't have to solve as general a problem as ought. Our tool can really use domain-specific knowledge to optimize the output and do the interpretation as an executable thing, and has all the meta notation that we use in the spec. So it's really designed to write the WebAssembly spec, and that vastly simplifies the problem. And we have way more control over what we are doing, and in particular what kind of output we are generating.
So there still is a tool called OT. People do still use it to ask So some of this is things that we might have wanted to do but totally didn't do. Some of these algorithmic generation things. But it looks as if the front end part is sort of a proper subset modulo syntax. Is that correct? Or is it really different?
Well, as I said, it's really designed to mirror the kind of meta notation we're using in the WebAssembly spec. So it has all these notational things like these overbar things and stars and different variations of that and sequences and stuff. So because we really want to produce a document that looks the same as before, right? So it might have been possible to tweak odd to the extent that it generates the same thing, but it might have been much harder. But in like on a abstract enough level, I assume you're right. It's kind of a subset of that.
There's one question which is interesting is the class of grammars that you need to let people write in order to parse the rules.
The class of grammars.
So a lot that you write a pretty much arbitrary text-free grammar.
Yeah.
And then you sort of made a GLR other for the language of rule.
So here it's more restricted. So syntactically you have like sequences of tokens, and then they are kind of disambiguated based on types. You're not totally freeform. I mean, this was actually like an important part that it's not like white space sensitive, for example, because of like differentliness. That was one part was important to us. But yeah, and that front end, that like all this disambiguating of the input syntax is kind of nasty, and I'm not particularly happy with that. It's probably much simpler than what OT has to do, but it's still like not simple.
Maybe in the interest of time.
Oh yeah, okay, I need to hurry up a little bit. Okay, so then you also have to write, of course, still write some editorial text manually, but mangling these three outputs together, you get the specification document, right? And briefly mentioning something about the timeline here. So what we have been working primarily on so far is like this first phase, and we maybe like 80%, 90% is like done with that. And then we have started kind of like the second phase now, which is porting over the mechanization parts. And then you could imagine like more work after that, or maybe in parallel that is concerned with test generation, which we haven't really started. thinking about how it reacts. So sort of my final slide is seeing the specifications and the talks about those earlier this week and the size of these, I was a bit surprised. So I actually looked up what the numbers are for the WebAssembly specification in SpecTech, and they're pretty small. And that includes everything except the details of numeric primitives. So it does not include yet like the formalization of IEEE floats essentially. But other than that, it's complete, like all the 500 instructions we are having in WASM 3, it's just like below 5,000 lines of code. And one kind of interesting discussion we could have is, or like, I would like to understand better why the difference is so large. Maybe I can understand 1 order of magnitude, but 2 orders of magnitude seems pretty excessive. I mean, clearly it's a simpler language because it's a higher level of abstraction, but even that doesn't really explain such a huge difference. To me anyway. I mean, maybe I'm being naive. Okay, I think that was it. So in terms of the questions that Peter posed in his email, adoption is something we have definitely managed. Hopefully forever, I don't know. I mean, there might still be, like you said, for RISC-V, a point where people say, oh, we're going to rip it out because bus factors are small. Organization, you could argue kind of we have figured it out, although it's maybe not super sustainable right now. Funding, of course, is no problem. I mean, most of this work is funded either by the companies, like implementing WebAssembly, and then by me, who's doing charity work, right? And of course, like universities who do research on that. Maintenance is, of course, also very much an open question, like how is this, can we do this long term? And in terms of not going mad, I don't know, you tell me. Okay, that's all I got.